We use sample statistics to estimate population parameters. Each time we take a random sample, the statistic will be just a little different. It will be close to the parameter, but it won't be exactly the same as the parameter. The sampling distribution tells us how likely it would be to get any particular value for this statistic. Most likely near the parameter, not so likely, but still possible to be far from the parameter. In other words, the sampling distribution tells us how much variability there is in our sample statistic from study to study. If you were watching closely, you may have noticed that we use the sampling distribution in two ways. First, we use the variability in the sampling distribution to construct confidence intervals that gave us a range of believable values for our population parameter based on our sample statistic. Second, we use the variability in the sampling distribution in statistical tests to determine how surprising the results from this study would be if a null hypothesis about the parameter were true. Since both confidence intervals and statistical tests are based on the sampling distribution, you might think that there's a link between them, and you'd be right. Turns out, you can use confidence intervals as a type of shortcut for conducting a statistical test, which is what we'll cover in this session. Think back to how we constructed confidence intervals. The general form for a confidence interval was the point estimate, that was your sample statistic, plus or minus the margin of error, which was the product of a critical value and the standard error. The critical value is the value of a random variable that corresponds to a particular tail probability of the sampling distribution. So if we wanted a 95% confidence interval, we found out how big x had to be so that the middle region that corresponded with x covered 95% of the sampling distribution. This value of x was the critical value that we used to create our confidence interval. This way, about 95% of the time we create an interval like this one, the population parameter will be somewhere in that interval, and 5% of the time the parameter won't be in that interval. Now let's think about our statistical tests. Most test statistics are a kind of standardized score. We take the distance between our test statistic and a null hypothesis value and divide by the standard error. Then, in a full version of the statistical test, we find the tail probability corresponding to that test statistic. We called that the p-value. If the p-value was less than our threshold of usualness, that is the significance level, in this class we use 0.05, we said that the evidence was pointing against the null hypothesis. Instead of calculating the exact p-value, we could have compared our test statistic with a critical value that corresponds with the significance level. This critical value was the largest our test statistic could be and still be considered usual. So if the test statistic was greater than the critical value, we knew that the result would be unusual if the null hypothesis were true. What similarities do you notice in these two procedures? They're both based on the sampling distribution. They both have a region of the sampling distribution that's considered usual. For the confidence interval, we use this region to construct a range of believable values for the parameter. For the statistical test, we use this region to decide whether our test statistic was unusual. For both, it was the critical value that corresponded to the confidence level or the significance level that gave us the boundary of usualness. And for the same confidence or significance level, the width of that region of usualness was the same. What's the difference between these two procedures? Well, for the confidence interval, we centered the sampling distribution on the sample statistic and focused on the usual region. For the statistical test, on the other hand, we centered the sampling distribution on the null hypothesis value and focused on the unusual region. So the big question is, how can we capitalize on the similarities between the confidence interval and the statistical test to use confidence intervals as a shortcut for statistical tests? In a statistical test, we look to see if our results would be unusual if the null hypothesis were true. In a confidence interval, we find the range of usual or believable values based on our results. To conduct a statistical test with a confidence interval, we want to look outside the confidence interval to the unusual region. To find statistically significant results in a statistical test, the test statistic has to be farther away from the null hypothesis value than the critical value. Since a confidence interval is centered on the test statistic instead of the null value, we flip this around when we use a confidence interval for inference. We look to see if the null hypothesis value is farther away from the sample statistic than the critical value, or more precisely than the confidence interval's margin of error, which of course is based on the critical value. So once we have a confidence interval from our study, we simply look to see if the null hypothesis value is covered in the range specified by the confidence interval. If the null hypothesis is in that region of believable values, then the results from our study wouldn't be all that unusual if the null hypothesis were true. And in that case, we don't have any evidence to be suspicious about the null hypothesis. We don't have enough evidence to convict the null hypothesis, so to speak. On the other hand, if the null hypothesis value is outside the confidence interval, the null hypothesis value is in the unusual region, and the results from this study would be unusual if the null hypothesis were true. So we start to become suspicious of the null hypothesis. That is, we reject the null hypothesis. We have evidence to support the alternative hypothesis. Let's look at how this works for our water well example. Instead of conducting the statistical test, let's construct a 95% confidence interval for the mean. We take the sample mean, 7.3, and add and subtract the margin of error, which is the 95% critical value, 2.03 here, multiplied by the standard error, in this case 0.32. This gives us a range of 6.66 up to 7.94. Now that we have our confidence interval, we can take the shortcut for our statistical test. We look to see if our null hypothesis value, 8, is inside the confidence interval. In this case, it isn't. Our results from this study would be unusual if the mean arsenic concentration in the well water was 8 parts per billion. So we conclude that the well water is safe for agricultural use. Or we could look at our work week example. Let's construct a 95% confidence interval for the average number of hours that women work. We take the sample mean, 39.1, and add and subtract the margin of error, which is the 95% critical value, in this case 1.97, multiplied by the standard error, 0.5 here. This gives us a range of 38.1 to 40.1. Now that we have our confidence interval, we can take the shortcut for the statistical test. We look to see if our null hypothesis value, 40, is inside the interval. In this case it is. It's just barely inside the interval, but it's less than 40.1, which is the upper end of the interval. So it's decidedly inside the interval. The results from this study would not be so unusual if women really did work 40 hours per week on average.